Ever wondered how AI systems like GPT or BERT achieve such human-like understanding? The answer lies in a revolutionary architecture that's redefining machine learning, the transformer. Today, we're diving deep into the technical heart of transformers, exploring their self-attention mechanisms, positional encoding, and why they've become the backbone of modern NLP. Let's break it down. Before transformers, recurrent neural networks (RNNs) and convolutional neural networks (CNNs) dominated sequence modeling. But they had critical limitations. RNNs struggled with long-term dependencies due to vanishing gradients, while CNNs relied on fixed receptive fields, making them inefficient for long sequences. These bottlenecks demanded a new approach, one that could parallelize computation and capture global dependencies. Enter the transformer, introduced in 2017 by Vaswani et al. Inattention is all you need. This paper replaced recurrence and convolutions with self-attention mechanisms, allowing the model to weigh relationships between all elements in a sequence simultaneously. The key innovation: a stack of encoder and decoder layers, each containing multi-head attention and feed-forward networks. Let's unpack self-attention. For each token in a sequence, the model generates three vectors: queries, keys, and values. The attention score between a query and key is calculated using a dot product, scaled by the square root of the key dimension. This score is then softmax normalized to produce weights, which are applied to the values to create a weighted sum. This process allows the model to dynamically focus on relevant parts of the input. But why multi-head? By splitting the attention computation into multiple heads, the model can capture diverse relationships. For example, one head might focus on syntactic structure, while another detects semantic roles. These heads are then concatenated and linearly transformed, enabling the model to learn complex hierarchical representations. Transformers don't have inherent sequence order, so positional encoding is added to inject information about token positions. This is typically done using sine and cosine functions of different frequencies, allowing the model to learn relative positions. The result: a way to preserve sequential context without recurrence. Each transformer layer also includes a feed-forward network, a simple two-layer MLP applied independently to each token. To stabilize training, layer normalization is applied after each sublayer, ensuring gradients remain well-behaved during backpropagation. The decoder builds on the encoder by adding a second attention mechanism to attend to the target sequence. This enables autoregressive generation, where each token is predicted based on previously generated tokens. The combination of encoder-decoder attention and self-attention in the decoder makes transformers powerful for tasks like machine translation and text generation. Transformers scale remarkably well with data and compute. Techniques like sparse attention and efficient attention variants, e.g., linformer performer, reduce quadratic complexity, making them feasible for long sequences. Meanwhile, parameter sharing across heads and layers ensures models like GPT-3, 175B parameters, remain trainable. From BERT to T5, transformers have become ubiquitous in NLP. But their influence extends beyond language. Vision transformers, ViTs, are now challenging CNNs in computer vision. As research progresses, we're seeing hybrid models, efficient variants, and even unsupervised pre-training advancements. The transformer isn't just a model, it's a paradigm shift. Thanks for watching, stay curious, and keep exploring the frontier of AI. Like this video, subscribe for more deep dives into AI research, and hit the bell for updates. What's your take on transformers? Drop a comment below.